Great. Yeah, I'll go through the paper and read it. I haven't actually read it before, but yeah. And people feel free to just stop me at any point and about things you're interested in. Yeah, I was. Nobody's presenting. I haven't read the paper. I just was. Unless someone else wants to present, I'll just read the paper out loud, and people can like stop me to comment things. But yeah, if someone has read the paper and is willing to present it or something, feel free to do it or say something. Otherwise, I'll just read it. Okay, nobody's saying anything, so I guess I have to read it. Okay, so let's see the abstract first. Yeah. Activation patching is a standard method in mechanistic interoperability for localizing the components of a model responsible for specific behaviors, but it is computationally expensive to apply at scale. Attribution patching offers a faster gradient-based approximation, yet suffers from a noise and reduced reliability in deep, highly nonlinear networks, which is most of the ones that people use in the practice. Okay, yeah. In this work, we reintroduce relevance patching, and it's RelP because it's relevant patching. Okay, makes sense. Which replaces the local gradients in attribution patching with propagation coefficients derived from layer-wise relevance propagation. Provides the network output backwards to the layers, distribution relevance. Right, so this is just a way of doing like something like gradient patching is a different kind of approximation to patching, which gets pretty computationally expensive. Okay. Distribution. Distribution relevance to lower level components according to local propagation rules that ensure properties such as relevance conservation or improve signal to noise ratio. Okay, I assume they'll explain what those are later. Like attribution patching, RelP requires only 2 forward passes and one backward pass, maintaining computational efficiency while improving faithfulness. I was thinking, oh yeah, 2 forward passes because it's doing the it's doing the corrupted and the not corrupted version for the patching. Uh, oh wait, the recording is not recording the screen. Let me change that. Okay. Anyway, never mind. Should be fixed now. Where was I? Yeah, sorry. Alex messaged me to tell me that the streaming in YouTube was not recording my screen. We okay. We validate. We validate RelP. Yeah, we already RelP against a range of models and tasks, showing that it's more accurately approximates activation patching than standard attribution patching. Particularly when analyzing residual stream and RelP outputs in the iterator objectification task. For GPT-2 large attribution patches, version correlation whatever 0.06, and this is 0.9, which is a higher number. I'm not sure what the contest, but yeah, that's higher number is very better. So yeah, makes sense. Essentially, we compare features, identified by RelP, integrated gradients, showing that represent and theories compare frames with tested parameter scores with integrated gradients. Okay, so they just do activation. This is like something like gradient patching, where you do some approximation of doing activation patching, which, in case someone doesn't know, is just you take some part of the model and like some head, and you run the model with two inputs, like one normal input and some input where it change something, and you try where the answer should be a different one, and you try finding which parts of the model, in which activations you can swap between the two to make it change the answer. And gradient patching is normally just a way of you do some gradient based approximation of which parts will change the output if changed. Uh, this is done instead of just doing activation patching, because if you want to do activation patching on all the different parts, you need to do a lot of forward. It's very computationally expensive, basically. So just doing an approximation is nice. And since this paper is mostly for the last step, since this paper is mostly, they found a nicer way of approximating things. Supposedly, we'll see how good it is, but yeah, they tested a bit and get nice scores, which is not always like necessarily mean much, depending on how well they did the baselines and all that. But yeah, maybe a good evidence that it works. Okay, let's see if the introduction. Anyone wants to say something? Do I keep going? Okay, I'll take the silence as I should just keep going. So yeah, this is the typical introduction thing where they say that mechanistic probability is very nice and whatever, and useful and whatever. Uh, layer wise. But it's also interesting because I didn't know. So I didn't know about this layer wise relevance preparation.
I'm also just in the process of skimming this paper right now, but they have a little bit more on layer-wise relevance propagation in the related work, but not a ton. They're kind of just like well, they kind of like broadly gesture like Taylor approximation, and then there's a quantity row, which we won't explain here. Yeah.
Yeah, so they do this. Yeah, so this is a previous method. I didn't know about it, but yeah, they do this RelP thing instead. This is this is the saying that method is very nice. They tried in a bunch of models. Most of them not like super big, but that makes sense because it's very expensive and hard to do it on. It's very expensive to do on large stuff with large models anyway. Look, yeah, precisely this kind of thing. I guess the interesting thing about this kind of approximation is to use it to embed the largest models and see if it works, because that's when you most really want to do some approximation instead of just attribution passing. But yeah. Anyway, this related works. They mention how much related works. Mention this layer-wise level preparation line. With analysis. Yeah, I have seen the previous things like HCDC, but I hadn't seen this new stuff which use gradient-based attributions. Maybe we can read some of those in future reading groups. But yeah, gradient-based propagation or gradient-based and propagation-based attribution methods. This is by input fetch for the magnitude. Vision feature maps. Yeah, I also don't know much about this gradient by inputs. I think we've seen maybe some paper that seems related to that in the past, but I don't completely remember it right now. Like something where I was confused because they multiply the gradient by the input, and maybe it's related to that. Anyway, background. From activation to attribution pattern, this is just an explanation of attribution pattern. This is mostly the thing I already explained before, I guess, with more math. Layer-wise relevance propagation is the other thing. Entre ideas to design. By the way, this idea is to assign a relevant score to each component of input feature, quantifying system contribution to the model's output to any metric defined for the output. Okay, and how it's that different from the syllabus scores and they propagated backwards to other networks according to layer-specific rules. Operation follows the principles of relevance conservation. Showing that the total relevance each layer is completely restored to the preceding layer, method attributing the chosen metric to the features. So basically, in this method, the relevance was up to some constant on each layer. Those inputs, no outputs. Okay, so for in some layer, okay, so they have this with the attribution layer. They have inputs represented to a layer by some function. For taking outputs. Okay. The first order Taylor expansion reference points versus that output does. the local Jacobian describe. Okay, so it has this formula. They do a sum of they are approximation a sum of like the j, which is the result of the function. No, the function. No. So multiplying. Okay, sorry, J is the Jacobian. They have the Jacobian multiplied by the activations plus some bias, and they have this. They are trying to approximate that with some function. The Jacobian describes how activations influence outputs, while B current constant steps are approximation errors. This decomposition motivates the distribution steps. Each component J in layer L is assigned to a relevance score, which is redistributed to its inputs in proportion to their contributions to the activation of component J. Okay. Here, the redistribution from upper layer activations to component I is first to the propagation coefficient. Here is the contributions from unconnected upper layer components. The relevance of components I layer L minus Y is given by relevances activations by this thing, which are parentheses the propagation coefficient. It depends on the local Jacobian, the activations, and the relevance score at layer L. Okay, at some filter determines which part of activations are considered relevant. Layer-based distribution of relevance can be represented in the input layer CSH or stop at the smith layer interest. The procedure begins with an initial relevant signal, typically defined using a metric computed from the model outputs, commonly the logit of true, this is kind of similar to, it is very similar to just taking the gradient, but they are doing this other operation with a Taylor expansion level. Right. Wait, but this is all explaining this layer-wise relevance, right? Wait, so yeah, the relevance patching is this. They replace the local gradients in attribution patching with propagation coefficients. So they just do patching with the same thing as doing patching, but with the layer-wise relevance propagation instead of with gradients. Okay. Yeah, I don't. Okay, so why is this better? Is the question. I guess they use my experience here. They might haven't still studied. Models preview the models offer face challenges when applied to large and wide networks. RelP mitigates these comments by propagating the network's output or any metric defined for example backflow through a network in a structured and theoretically grounded manner. Well, I mean, doing a gradient is also structured and theoretically grounded, I guess. I don't know why this is. Okay, depending on the layers, given a model architecture, different propagation rules can be proposed. This is, I mean, this seems a bit more annoying than doing gradient approximations then, because with the gradient approximations they just work with any, just do the same thing with any kind of network, and you have to figure out some specific way, like some specific gradient propagation rule for each architecture that will be maybe annoying. Although I guess in practice, people just have to figure that out for the use architectures, and it should be easy to have some library that just does it. But still, maybe it's slightly more annoying to implement. Especially if you are using it some weird new architecture or something. Can typically derive from gradient analysis of model components. Versus guided with common design of expansion, so sparsity, reduce noise, and relevance conservation. Ajá. Moreover, specialized propagation rules have been developed to handle diverse nonlinear. Someone is writing. Right. I guess it says something. So I guess it makes sense that, like, if you are doing a gradient based approximation, you are kind of assuming it's linear, and you might not be dealing with, you're basically not really dealing with the nonlinearities that much. So maybe I can see why, if you do some specific propagation rule or whatever for your activation functions or whatever, that might get better results. I don't think I understand really like this, how this whole LRP thing works in terms of math right now, to get that more than that. But yeah. Anyway, yeah, I see you're still typing on the chat. I'll just keep going. What you got? Across deep network families, yeah, search specialists from models are shown in table 1. Attribution patching also relies on gradients to approximate the effect of substituting heading activations, patching in, which makes it susceptible to the noise and approximation errors inherent to gradient-based attribution methods, particularly in very large models. To address this, we introduce relevance patching. Yeah, this is the thing that you already explained earlier. Formally reinforces the structure of standard attribution patching. Anyway, formally, some patching in ATP, the contribution of component is computed as the dot product between change in activation caused by replacing the original input with a patch input, and the gradient of the metric with respect to the component. Yeah. Evaluated to the original input. RelP modifies the. I didn't remember that detail about the implementation of attribution patching. RelP modifies this process by substituting the gradient term with the RelP derived promotion coefficient for that component. The resulting contribution score is defined as this formula. Yeah, this I still don't completely understand how that formula. Prevention coefficient and the relevance score for a component. RelP perceives the efficiency of attribution patterns while proving fight for it. So at least they claim that. Unlike Marx et al., which relies on integrated gradients for model-correlated approximation at a higher computational cost. Yeah, I don't know what integrated gradients is, but okay. RelP provides a scalable and faithful localization for influential components. Propagation rules. Okay, here's the propagation rules. I guess this thing is, instead of doing a gradient, you are using propagation rules to calculate some coefficient. Answering to the thing that someone wrote on the chat, I think it's something like that. But I don't understand it very well either yet. But I'm getting the sense is that because they basically said they replace like this, the gradient with this gradient coefficient, right? And the gradient coefficient seems to come from these propagation rules. Also, they do this Jacobian whatever, I don't know exactly what they're doing there. But these propagation rules, and the propagation rules are basically handcrafted for the model, the architecture, if I understanding correctly. So it might be that. It could be a nice, like if it works better than doing gradients in general, that would be nice. I could also be okay. I will be worried about whether their half-baked rules are like actually work or they are not accidentally overfitted to their test or something. But it depends on how they pick them. Maybe they have some theoretical. I think they mentioned something. They might have some theoretical good reasons to pick those rules and not others. Maybe they work. We'll see what they say on propagation rules. But I think your description might. It's also something like my impression of the paper so far, or like what they are saying. Anyway, let's keep going, I guess. Tamil one, summarize the supervisor rules, applicable to composition transformer. Okay, so they also have, right, I think they mentioned before, they have different rules for like the different components. I guess they mean the attention and they propagate different through the MLPs or whatever, which makes sense.
This paper is mostly, if I understand it correctly, just finding ways to make activation caching cheaper, right? By making a new method to do it.
I think it's not cheaper. It's just supposed to be work better. Sorry, no, you're right. Sorry, I misunderstood. Yes, it's there is already a way of doing activation patching cheaper, which is attribution patching. But it doesn't work very well. They are trying to find another way. This is supposed to be another way that is as expensive, like as cheap as attribution patching, which is like it's the cheap version of activation patching. So you were right. But it's supposed to work, like do a better approximation.
Makes sense.
Because if you want to do activation patching directly, it becomes really bad with big models because you need to check like the contribution of all components on each component, and that it's bad really quickly. It just doesn't scale. Anyway. I see you are still writing, but I'll read the propagation rules while you write. Inattention has this, or no, feel free to just talk on voice if you prefer. Just interrupt me at any point. Relations between terms, compare conservation and the AH rule, preserves by the attention push dependent on pay attention weights, which are also input dependent. Correlations between these terms can break conservation, and the AA's rule preserves by treating heads. I'm not sure I understand this line. Centering evidence the scanning can cause relevance collapse. Yeah, so they are dying a bunch of specific stuff for each thing that I don't completely understand. It all seems like the thing they are doing is, in fact, hand writing some specific rules to replace gradient with some supposed better approximation for each component. Based on like doing a specific thing for each layer. Conservation functions can disrupt conservation since their output is not linear. The transformation on the input, and the relative between the nonlinear component as constant. I don't know what that means either, but okay. Zero risk going to the gradient. Yeah, I also don't know what the gradient multiplied by input thing is. Yeah. I guess these rules are supposed to be on some table. Here it is. Yeah, and then rule implementation trick. Okay, yeah, so they have different rules for each. And they cite some other work on this layer-wise relevance propagation, which. So I guess some other paper already invented this. Like people had already invented this layer-wise relevance propagation thing, and this is just. This paper is just let's use it for activation patching and see what happens. And my guess is those other papers were like, I will have to read it, but without reading, I will guess they're probably explainable AI kinds of paper. where they are mostly trying to look into how it affects the input. It's kind of a bit. I mean, it's kind of. I didn't like the whole. Let's try to figure out which parts of the input matter for some output thing. I think that's some users, but it's mostly just confusing and meaningless. I mean, because it makes some sense in some image things, but I think people are probably not. The whole thing is probably a lot of waste time. Well, yeah, sorry. Activation patching, relations, layer-wise relevance patching. Yes, that's a good explanation. Let me wait a moment. Let me put your text, so your chat is on the YouTube video. So people see what you are talking about. Yeah. So anyway, going back to this. Propagation rules. So yeah, the propagation rules are just they're rules that they made for each layer. Not going to get into trying to understand all of them, right? But they probably make some sense. Like there seems to be some simple things that probably make some theoretical sense for like each layer. And it has some explanations, but I don't think it's super interesting to go into that unless someone wants to actually build on this work and like try to come up with rules for some other model. I think if you want to do that, you should probably read this paper again and like all of the other and the previous work or whatever. Like if I at some point want to do the patching, I could try this to see if it works better. But yeah, I feel like right now I mostly would use their rules and assume they make sense. uh, Evaluate different types of rail by messing it out, attribution patching. Yeah, so I do like better from the gradient patch, at least for now, is that I have a pretty good idea of how gradient patching works because you just take the gradient and it's like it's a better sense of when that works or not. And these rules are more complicated than the simple approach of just take the gradient. And I like that a bit less because it feels like there's more room for like, for example, messing up if you have to implement it yourself. But if it works better, that's nice. And this definitely feels the kind of thing I would like to just have some implementation library that does it. Uh, we Pricing, pricing on the indirect target duplication task. Yeah, so they do a bunch of experiments and different models. And yeah, and the indirect target duplication is nice because we mostly have some idea of how it works from other people trying. And there's a bunch of other papers on it, so it works as a benchmark, kind of. It's not like we have, unfortunately, it's not like we have a ground truth of like how the indirect identification task should look like. But I guess you have ground truth of you can do attribution patching and see how well it's on the indirect identification task. Yeah. We control so handle compliance. Each pair consists of an original prompt. Yeah, this is just the typical elements. Also, it makes sense. The biggest model they tried is 7 billion if they have to also calculate the attribution, get the activation patching, before attribution patching to compare. Which I'm guessing is that they do, but let's see. Okay, so they do it and they get better numbers. We'll see the graphs, but there's the reference between attribution patching and RelP. Attribution patching and RelP published in Farnoush. Attribution patching. Okay, so there's a paper out, Neel's paper out, attribution patching. First noted the stream prepared with large attributions of the nonlinearity introduced by the unknown, which simplifically disrupts the underlying linear approximation. Thus performs poorly on RelP0 since its layer in GPT-2 small functions are extended embedding. And Nanda, yeah, this was in paper, so the linear approximation in this layer may become unstable. Leading to misleading insights. I don't know if we have read this Neel paper there is, I think. No, this is just the. Yeah, no, sorry. Yeah, we have. It's just the attribution patching. No, it's not the paper, it's just the attribution patching page on Neel's blog, which basically when he introduced the thing. I think it's funny that probably a lot of papers are going to have, and probably already are, citing Neel's personal blog thing as a source, because it's actually the source for that. I think I might have cited the Les Brown post for it on my paper.
I was gonna say that like maybe citing less wrong is like funnier than citing a blog. I'm not sure though.
Yeah. You kind of
At least the
have to, because
requirements
it's
to post a lot strong. They at least like it's not like a post where anybody can post. Like at least you have to get it like meet the requirements at least.
Oh, but anyone can post in this blog though.
I guess you can, but
You can just make an account and post. But yeah, it is. Anyone can posting. Well, not exactly. You have to have someone that gives you. There's an invitation on the other how it works, but mostly it's not very hard for someone to post in a paper in archive video. So it's not like it's more. It's not like it's a conference or something. But yeah, it is funny that you kind of have, for some Mech Interp things, the source of the method is on some Les Brown post or something like that, and you kind of have to cite it. Anyway, well, we find that the proposed method consistently achieves strong correlations with activation patching and is often clearly superior to the standard activation patching. This underscores the effectiveness of the tiny proportion rules. Yeah, I hope they just thought of the rules because of. I guess it. Well, I guess if they were citing the original paper, so the rules probably don't come from trying rules until they got good scores. So in some sense, so we can say they are not overfit to the indirect object justification task because the original paper was focused on some of the explainable, I think, with images probably. Well, not if it was a transformer. I don't know. Not going to bother reading it right now. Yeah. Probably just the typical activation patching thing. This reminds me of when I was doing this for my paper, and I also have this kind of graphs. Something that's like a problem with this kind of thing is I guess it works to know when to like if you just care about which layers and which parts of the residual stream matter. That it kind of works. If you wanted to use something like patching attribution patching to figure out more granularly which parts of the model do specific things, they kind of do that. I guess they probably do that later for the when they compare with these circuit search things. A problem is not even related to the patching or whatever. It's it's which parts of the model do you patch? Because I guess you can just patch heads, right? But that's sneaking into the assumption that like each attention head does some specific thing, and you can isolate, like you can use the heads as a behavior as the the units of behavior. You can also use like if you really want to, you definitely need to do something like attribution patching for this. You could do it on each neuron too, but there is the whole superposition thing. So I guess if we want, I feel like to do get good Mech Interp results, we need a mix of good patching methods and good ways of like dividing up the model, like the Spartan calls or whatever, to do patching on. You got that, like if you got some way of dividing the modeling, individually meaningful units, and you just had some methods, something like seems like something like doing a CDC or whatever. Maybe with some approximation like this instead of just doing it directly might just work and like give you some interesting diagram that shows you how the model does things, kind of like the Anthropic paper where they did all those that they were using transcoders and doing something like that. I don't remember what they were using to do the actual figure out which parts did what. I think maybe just manually look at them. I don't know. I don't remember. But yeah, I guess going to that, I guess that I was really saying it because I thought about it, but I guess this next part of the paper is about this. Okay, sparse feature circuit for selected paper. Yeah. Yeah, they talk about what sparse circuits are. A ver, the grammatical number of its subset. To identify and analyze the circuits, we use feature discovery using sparse encoders. Yeah, this is the thing I was saying. That you did this with sparse encoders. So there is like a thing where to do this kind of thing better, you need both better patching methods and better ways of dividing better spice sparse encoder kind of things. Because current sparse encoders are not super good. Yeah. Assess the influence on the model's output employed efficiently in permissions to patterns and patterns. Instead, the contribution with feature ventilations. Also, I didn't look much at this, but yeah, this is just the graph. Say like they have activation patching, relevance patching, attribution patching, and the activation, like the relevance patching is closer to the activation patching. I wonder how much they look at different examples until it matches. Like I picked the one that looked better. But yeah. In this case, this one actually looks a bit closer. Well, it depends. It's missing this thing. Anyway. Wait, yeah, they're using backmodel comments. I think that might be a 3. Yeah, that might be just attribution patching. I think. I don't. Yeah. So yeah, you could just replace that with this relevance patching thing. Like I don't. You just it's basically the same thing. You are doing like you're just using a different score. So you could just swap it. Maybe, and if it works better, that could make the whole like you could do it on the. I think it would be interesting to see like if there is some things that look clearer if you do the if you do the anthropic paper with the thing, but unfortunately, I guess you will have to do it in another model, but I think they do it on Cloud, and that's not possible for me. I don't know if the code is even public. Oh, I think the Rezaei people were replicating it, the anthropic stuff on other models, maybe, if I remember correctly. I think Gonzalo said something like that. So maybe there is some Eleuthère work on doing the same kind of analysis on PC or whatever. And it could be interesting to see if using this method gets different results.
Yeah, I'm wondering actually, because there is the open source implementation of circuit tracing. So this might be an interesting thing.
I've been struggling to implement the open source version of circuit tracing actually.
Wait, implement it or run it? Because there's
running it.
Yeah, I'm trying to run it for one of the models I'm trying to look at, and I'm getting CUDA out of memory issues with the attribute.
I see. There's like a GitHub issue somewhere where someone's like, I'm trying to use Quen.
Yeah, that's me.
4 billion.
No. I said 14 billion. That's me.
Okay. Do you have sparse encoders for that?
I used the Anthropic Fellow transcoders that were already pre-trained to try recreating the model from the Thought Anchors paper. So I'm trying to see. So I found a circuit with the Thought Anchors paper, and I'm just trying to look at attribution graph with it to see if I can find any behaviors. The problem I have right now is the CUDA out of memory issue with attribution.
Yeah, there's
graphs.
someone who made a GitHub issue about this. So
no, that's me.
Like on the very first. No, like on the very first. Are you Doc?
No, I'm Realmberg. I'm Realmberg.
Yeah. Okay. Yeah. This is okay. The GitHub issue I'm talking about is like from like maybe a few weeks after the repo is released. But like the person's like, okay, yeah, I slightly changed the implementation to like lazily load things in and out, and I think this is now part of the this is now part of the like main branch. Like there's in the command line you can specify an argument for like lazy.
Yeah.
Or like
I tried lazy loading. It did not fix it.
Yeah.
Lazy loading did not.
Okay.
I tried lowering the max features in the batch size actually. I so far tried a H200 with on Vast with 140 VRAM. So it might be something to do with attribute, or maybe just the model's too big.
Yeah, I guess. Yeah.
I guess I'll put that on my Neel app. I guess I'll just say like I just can't fix the computer.
Yeah.
Well, at the very least, I found a unique behavior with counterfactual importance and plan generation.
Cool if someone like someone implements this method on the.
I'm slightly considering it, but I need to think about how much like. Question in chat about the GitHub link for circuit tracing. Yes, I can send a link.
Yeah, I tried the other library. The attribute from a Luther AI. I haven't tried that yet fully. That one's not I'm not 100% sure if it works. I tried it. It just gave me errors, so I just don't know how to use it. The docs are non-existent for that one. Yeah, I know like there's two circuit tracing libraries. One made the Anthropic one, the other is the Luther AI attribute one. But I think the Luther AI one, I don't know how to use it because there's no docs on it.
Yeah, I mean, if no one wants to, it could be.
The main critique I have about Circuit Tracer, it is all on Transformer Lens. So I had to make and move it on PyTorch hooks to because if it's on Transformer Lens, it has to all be on one GPU. It doesn't support Accelerate. Yeah, I think there needs to be some fix on the attribution graph to make it so you can like do like device map auto on it or something. Because so far it all goes on GPU 0. And I can't fix it. I tried reducing it by moving the transcoder code to use PyTorch hooks, but attribute seems to put it all on GPU 0.
Anyway, going back to this, yeah, I at the same time, this also seems the kind of thing that, even assuming it does work better and whatever, it might be the kind of thing that in a few months someone will post some even better method that works differently or something, and they will like kind of like when people started doing stuff personal coders, and soon there were like a lot of variants. Maybe people now will start doing better approximations of gradient patching, and Maybe if you spend a lot of time trying to implement this, by the time you finish, there will be something else. I don't know. But maybe this is the kind of thing where you can just, write a few lines of code replacing the gradient part with doing some. Although I think that something annoying might be that the whole gradient thing, there is a lot of PyTorch stuff that just does it. That just does a lot of work for you, and you will probably have to rewrite stuff for this. But maybe they have code. I don't know if this paper has code, or maybe the original paper for the approximation, well, LR, whatever, what has code. So maybe it's just a question of copy pasting the code. A problem is also like I don't know for this if you have some. I haven't read that data either. We could. Yeah, I was not super paying a lot of attention on hours because I was kind of on holidays. We could read it like next reading group or something. Uh, yeah, I'll take a look at it and maybe we can read it on this. Uh, Anyways, kind of let's finish this paper out. I kind of want to. So let's see. Okay, so they do the sparse circuit thing. Nature circuit, completeness, faithfulness. And they do the typical thing of look how better our method is. So red lines are the new thing, and green lines are the old thing. Doesn't it is kind of confusing. It doesn't seem like it's obviously better, right? Because oh no, this is not this is the more expensive. Oh, I guess the idea is that you get similar results, but you this is more cheap than the other. Can't you do with this with attribution patching though instead of the integrated grades? If so, they could have also compared to that. I was the value of it. Anyway, faithfulness. Anyway, limitations and future work. Yeah, conclusion. Yeah, the conclusion just said their method is better. Well, in the sparse circuit, they didn't show that their method is better. They showed that the method is around the same as the other and the integrated gradients thing. Integrated gradients is like close, it's a more expensive approximation. So there they are claiming that the method is less expensive than the other. Yeah, I also don't know about transcoders, but I do know that I think the Eluther people have and also transcoders for some models. Maybe there are I think there are some kind of sparse encoder, but I don't know if they are transcoders. Like that DeepMind released at some point for Gemma, if I remember correctly. But yeah, no idea. Maybe it's on the circuit research landscape thing. So. It's nice. So they are for Quen and Lama and Gemma, I see. I don't think, yeah, there is not a lot more to talk about this paper, I think, by the way. So basically, it is. Oh, wait a minute. The images are very areas. I have semantically elaborate labels. Models don't have labels, they're just indices. Index related files. Okay, makes sense. Anyway, so about this paper, yeah, so for what I understood, it is basically the thing we were saying earlier, that it's just they do something like attribution patching, but instead of doing attribution, they do these other specific rules for each part of the model, where instead of just doing back propagation through all of them, they do some other function that they have a function for the attention, a function for the activation functions and so on. Try to have a better approximation, and they basically handcraft those based on some theoretical considerations that I didn't really understand, and which probably makes sense. And they then tested it and got slightly better approximation, somewhat better approximation of the attribution patching. Sorry, of the original activation patching than with attribution patching. And that's basically it, I guess. I don't really have much else to say about it. As I close my. I see people are still writing on the chat. But
Yeah, I think the writing's probably not directly related to the paper. It's maybe
yeah,
just,
probably it's about
interpretation stuff.
the yeah. So you are going to talk about the other stuff like the transcoders and that. I think we can get the end the reading group on that now. But yeah, feel free to keep to stay here and talk about the transcoder stuff.
Okay, yeah, sounds good. Thanks.